Hello everyone. In this lecture, we are going to proceed on discussion about halogenation, and now we will discuss an interesting case of allylic halogenation. So, firstly, we will see that what is the allylic halogenation and what is the allylic carbon. So, about which we are discussing that how this undergoes the halogenation and we can convert it into any of the allyl chloride or allyl bromide one. So in this slide, if you just look at this one, so this introductory slide is giving you the hint about what kind of reaction we are going to discuss in our this discussion. So here this is one of the alkene which is reacting with one of the halogen at a very high temperature. And then we are getting a product in a form of that we are getting one kind of alkynyl halogen product, and that is the 3-chloropropene, or in common words, we say allyl chloride or allyl chloride. And the HCl is a side product which is produced here. Now, the question is this one, that whenever we are talking about the alkenes, which are the unsaturated hydrocarbons or the alkanes one, and if they are reacting with the halogens, that is a chlorine or bromine, so they can easily undergo the addition reaction. Addition reaction means that there could be the attack and addition of that halogen at the pi bond, which is a double bond here. So we can simply get the 2 chlorine attached on that one in a subsequent step. For the at the very first step, there will be the 1 chlorine addition, and then it will prolong, and there will be another chlorine if we have the surplus or enough amount or the concentration of the chlorine here. But that equation is giving us a bizarre information that it is not going through the addition reaction. So this is going through some kind of substitution reaction. So I will define later that what is a substitution reaction step by step, so you can build your concept that firstly, if you are able to recognize and establish the fact that what is the allylic carbon, right? So now one thing we have established initially, that when we are treating alkenes at a elevated temperature, so this is not going through the addition reaction. So there must be some reason that why it is not going or not giving the addition reaction. So after the addition reaction, what kind of product we should get is the halogenated alkanes, because there is a pi bond, the double bond will broken, and there will be the addition of that halogen and the addition of hydrogen here. So then we will get the alkanes, because this is simply the additive product, that the what we are reacting is that is the part of that product. So now moving to next, the first thing is this one, that what the allylic carbon is. So the allylic carbon is the carbon next to a carbon-carbon double bond, right? So if we just look at this example, this is the propene, and in a more explained or detailed name, IUPAC name, this is the 1-propene, or you can say the prop-1-ene. So this is the propene structure, and you can see there is a double bond between a carbon-1 and carbon-2, right? So what is the allylic carbon according to the definition? Yes, so that CH3, which is on a one side, this is not the part of the double bond, but this is just adjacent, and this is next to the carbon, which is making double bond, right? So that is the allylic carbon. The carbon which is involved in a double bond, so in a common terminology or in a native names, we term it as a vinylic, right? So this is the vinylic carbon, and the carbon which is adjacent to the double bonded carbon is the allylic carbon. So now the important thing which I want to emphasize and I need your attention is this one, that when we treat, and here this is an example, this is the propene, when we treat the propene with the chlorine at the room temperature, or in the presence of the light. So what will happen is that it will easily undergo the addition reaction, right? So here I have written the product after the two steps, because in a very first step, what will happen, that there will be the attachment of the Cl, and there will be the attachment of there will be HCl which will be produced, and if it is continue, right, so then there will be another addition of the Cl where that was involved in the double bond, right? So that may be the single halogenated product, and if you prolong that one, so you can have the two or the dihalogenated or dichlorinated product as well, right? So now, if you just look at this one, that when we treat it with at the elevated temperature, so an interesting and a different thing the chemist has observed, that at the very high temperature or elevated temperature, the alkenes or the propene is behaving differently. So this is not giving you the addition reaction mechanism, while this is giving you the product, which is the allyl product, right? Or which is the alkenyl or halogenated alkenes, which you are getting, or the you can say the haloalkenes, right? Which you are getting as a product. So now the thing is this, from this slide, we can establish that through the experiment, this has conducted that your product, you can aimed, or you can design a product, or objective of a product could be achieved by changing the reaction mechanism, basically by changing the conditions of the reaction. So you can force the reactant or the starting material to behave differently, right? So this alkene is at the room temperature is giving you the addition reaction, but at the elevated temperature, this is giving you the alkenyl alkenyl or allyl product, right, with the halogen substitution. Now this second kind of reaction is basically substitution reaction. And when we have the case, the simplest example of the allyl is the propene, because there is the doubly bonded carbon, and there is a third carbon which is just adjacent to this one. So you can have the allyl carbon in a longer chain as well, but you have to focus that which one is the allylic carbon. So the carbon which is just next to the carbon double bonded carbon, right? So the first one is a kind of addition reaction, while the second type is basically the allylic substitution. So allylic substitution is any reaction in which an atom or group of atom is substituted for another atom or group of atoms at an allylic carbon. So now, what was the substitution here you have observed? So basically, we have treated it with the Cl2. So what has happened here, that one of the hydrogen of this CH3 has substituted with one of the Cl from this one. So what we get in a product is that we have achieved this 3-chloroprop-1-ene or 3-chloropropene, right? And plus we also have HCl, right? And how that HCl has achieved there. So this was a Cl2, right? So the one Cl has substituted this hydrogen of this methyl, and one when the hydrogen and carbon bond has broken, so this has been taken by this Cl, and we have get this HCl product, right? So next is this one. Why at the elevated temperature, we are experiencing that this is undergoing to the allylic radical, and we are getting the allylic product rather than the addition reaction, or in another simple way, why we are getting the allylic substitution reaction rather the addition reaction at the elevated temperature, right? So for this, I need your attention for that structure, right? This is a structure or proper open structure in a spatial rearrangement, mentioning its TU as well. The arrangement of the groups, like where this hydrogen is fronting or backward. So this is the propene structure. And here you can see that if we break this carbon hydrogen bond, so it demands 372 kilojoules per mole. And I have told you that the plus sign is for the endothermic reaction. So whenever you are breaking the bond, so it means there's some kind of energy you are providing to the system. So here, if you just compare this one, when we are interested to break the carbon hydrogen bond with this doubly bonded, so it demands the high amount of energy. So another relationship between the bond association energy and the radical stabilization is this one, that if we demands a higher amount of energy to break certain bond, so it means that radical, the radical or cation or anion which is forming after breaking that bond is not as stable as the other one. So definitely you always go for that kind of transition or the shape when this demands you will always prefer that route which where you can achieve the product or the you can get your destination, but comparatively more smarter work or the less effort as compared to the very hard effort. So that is happening, that in this reaction, when we are providing the temperature, so this bond breaking is far easier as compared to this one. And the reason is this one, that if we have this allylic radical, this is more stable as compared to the vinylic radical. So just focus on the stable and the values I want to identify by encircling this with a red line border is this one, that the first one is this is the propene, right? And when it is converted, this is the hydrocarbon, the original starting material, the reagent from which we are producing the radical, right? So this is a hydrocarbon and that is a propene. When it converts into the radical, so this is the CH2 radical, and this radical name is allyl or allylic, right? So a type of radical is allylic radical, and this is most stable radical. If you just look at this at the head of this arrow, so this is pointing that the radical stability is increasing upward. So the least stable one is the vinylic radical, right? So if we break that bond, so this is generating the vinylic radical, while if that bond has broken, so then it is creating the allylic radical. So allylic radical is more stable as compared to the vinylic radical. So that's why the carbon hydrogen bond breaking for generating this radical is demanding uh, much less energy as compared to this one, right? So the because of the stabilization of allylic radical, when we are providing that elevated temperature, so this goes through that bond breaking, which is generating the allylic radical. So the next thing is this one, that if you just look at the previous slide, so where I mentioned the temperature, so the temperature here was the 350 degrees C. And if you have to do that, you have to provide that temperature in your lab. So this is much expensive and this is harder to achieve, right? So then the chemists and the scientists have worked for finding out a way that we can generate the allylic halogens, right? Or the alkyl halides, haloalkenes, with the some kind of reagent, by combining with some kind of reagent, that it is giving us the halogen source, but it is not requiring that amount of energy that we have to provide the 350 degrees C, because uh, why we are avoiding the temperature, because for providing too high temperature, you demand special equipment to that high temperature, and definitely then the solvents have their some boiling point, and at very elevated temperature. So what would be the suitable solvent which you have to use that it can stain and it is not degrading or drying at the 350 degrees C? So that is harder to achieve. So that's why for the normal solvent use, the scientist has developed a reagent which is a very useful reagent, and this is very specific in a way that we can generate the allylic product by combining the NBS with with any of the alkenes. So the purpose is this meant that by using the N-Bromosuccinamide in dichloromethane is a solvent for that reaction in which we are carrying out this reaction. So the reaction between an alkene and NBS is most commonly initiated by light. So just by the light, this NBS, which is the N-Bromosuccinamide, so this is behaving as an initiator, and this is providing this bromine radical to the system, right? So this reaction involves a net double substitution, a bromine in NBS and a hydrogen in the alkene exchange take place, right? So that's why this is called the double substitution. This is not a single substitution. So they are exchanging with each other. So that's why this is called the double substitution. But now what is happening, that at the just above the room temperature, we can just simply carry out this reaction with the normal solvent. One of the most common solvent which we use in synthetic chemistry is the CH2Cl2 dichloromethane, right? So the overall reaction is this one, that we are treating any of the alkene. Here, this is an example of a cycloalkene, and this is the cyclohexene because there is a six carbon chain, which is closed ring shape. So that's why we use the prefix cyclo for this one. So cyclohexene is reacting with NBS, which is our N-Bromosuccinamide, in the presence of light and a solvent, organic solvent, which is a dichloromethane. So we get the bromocyclohexene as a product, and this is the succinamide. Now, if you just look at this one here in a bracket, this is mentioned that this is a racemic. So racemic mixture means that there are the different possibilities in a spatial rearrangement and the stereochemistry base. So then there could be the S or R, and I will discuss with you that what are these stereo isomers. So it means that they are the very closely related and the different isomers we are getting in a same reaction mixture. So we term it as a racemic. When this is a pure product, like either the one kind of isomer is there, so then this is the, we just mentioned that product completely, but the racemic means that this is a mixture of more than one isomers in a reaction mixture. So now we will see that what is the overall mechanism of proceeding the halogenation of any of the alkene in the presence of NBS, right? So just it followed the same kind of reaction radical chain mechanism as we did with the alkenes, and that was having the three main steps. First was the chain initiation, second was chain propagation, and third was the chain termination. So the similar steps are happening there, but the only thing different is this one, that we are not using the Br2 or Cl2 or HCl or HBr as source of the halogen, while we are using the NBS. And another thing is this one, that now we are treating it with the alkene, and the substitution will happen at the allylic carbon, not on the carbon doubly bonded carbons, right? So this is not the simple carbon hydrogen bond. This is basically the allylic carbon hydrogen bond which will be broken, and then we will get the attachment of the bromine or chlorine, whatever the halogen we are providing is. So that will attach to that one. So here we are using the NBS, which is the bromosuccinamide. So we are expecting the brominated products, right, or the bromo products after treating or alkene with that NBS. So the first step is in the mechanism is the chain initiation. So chain initiation involves formation of radical from NBS by light induced homolytic cleavage. So light induced means that is energized, it is instigated, or it is activated by the light, right? And homolytic cleavage, as we have discussed in a previous lecture, that when the bond is breaking in a way that the both bonded atoms are taking their equal share. And the equal share means that the one bond means there is a pair of electron. So every atom is getting the single electron from this one. And how we are showing that homolytic cleavage is through the fish hook arrow, right? So if I just go for the pen, so to just to mention that one, that how that was cleaving is, that is the fish hook arrow, right? And we are getting the N-succinamide radical, and there is the bromine radical. So this was the initiation step, and this is a chain initiation, and the NBS firstly go through the initiation step by the light, and then it is giving you the Br radical. Now we will see what is happening next. So the next step is the chain propagation. So we get in a system, we have the here we have the Br radical, which has generated from the NBS. And now we have our starting material, that is the propene, right? And this bromine radical, which has initiated already from the first step, is instigating this propene to break that, to break that bond, and then it will give you the that carbon and hydrogen bond will broken through the homolytic cleavage, right? And then there is the allylic or the allyl radical is formed plus HBr. Now this is a propagation, that the one radical is inducing or instigating another neutral species to become the radical. So here, and this allyl radical is instigating this Br2 to break its bond and then convert into the Br radical, because it needs some radical to combine with that one. So then we will have this bromo, right, 3-bromo propene as our product, and then again there is a Br radical. Now the question could be there, that how, from where this Br comes, though we were not providing Br2, so from where this Br2 has generated. So basically what is happening, that then when the Br radical is formed from the NBS, so it is continuously generating in the system. So there is a Br radical in a system, there is another Br radical in a system, because we are not providing only the one molecule of this one. So there are number of molecules present in certain amount of that NBS. So they are continuously giving the Br radical in the system. So when the Br radical are combining both Br radicals, so they are converting into the Br2, right? So this neutral species then instigated by this allyl radical to break its bond, and then to become the part of it, right? So note that, as always, this combination of chain propagation steps add up to the observed stoichiometry. This reaction is exactly like halogenation of alkenes, but is strongly regioselective for allylic hydrogen because of its weak bond, right? So we have established that fact because allylic carbon hydrogen bond is weaker as compared to the CH double bond CH, right? So that's why this is basically propagating in a way whenever there is allylic radical will be formed, right? And it also depends that it is a very controlled in a way, because NBS is a source which is providing the BR very slowly. So this is not like the if we just use the Br2 or the Cl2. So this is and visually, if you just look at this one, so this is giving the half of that one, what we were assuming with the Br2, if we are providing that one, right? So that's why it is going through this mechanism, that it will go for the allylic radical formation, and then this allylic radical will combine with the Br radical to make this haloalkene, so or bromoalkene, right? So now the third step is the chain termination. So whatever the radicals has formed in the reaction mixtures, we already have discussed in a previous lecture where we talk about the halogenation of the alkanes. So the radicals which are forming in the reaction mixture, they just combine whatever is coming in their path to become the stable and the neutral species. So they are we come with all kind of combinations and all kind of opportunities and the possibilities of the product. So the first thing is this one, that the Br radical is there, so another Br radical will combine and it will convert into the Br2, and this Br2 is again becoming the part of the cycle, and this was combining with the allylic radical, and then we were having our bromo propene as a product. Now the again, this is also the part of our chain propagation step, and this is also the step involved in our chain termination as well. Then if the two allylic radical combines, so they will get the alkenes, there the multiple double bonds in a chain, but it will extend the chain length as it do as in the alkenes. So the bromine Br2 necessary for step 2 is formed by the reaction of product HBr with NBS. What I was telling you, that there you don't need to confuse that we are not providing the Br2 initially. So from where that comes? So that comes by the combination of this one, that the NBr is giving that Br radical, and the HBr was formed in the system because that the Br is combining with another one. So then this Br2 has formed, or if you can just write with the this Br2, because you know that if the both Br radical are in the system, so they are combining in that one. So this is the reaction which is happening in a reaction mixture. So you don't need to worry about this one. And if you just write this Br radical, even then that is fine, that this is coming from the NBS. So you don't need to write in a form of the Br2. You can just mention this as a Br radical, but the need is this one, that you should know that what kind of events can happen in the reaction system, because there are a number of molecules and there are all kind of radicals which are forming in the system. So all these combinations can happen, and you will see these in your products, right, as a minor or as a major. So next is the at last but not least is your task, that you have to apply what we have discussed today about NBS as a source of the bromine, and a reaction where we are retaining the double bond, we are not disturbing the double bond, but we are getting our alkyl halides, and this alkyl halide is basically our haloalkene, where we are having the alkene as our hydrocarbon, and our bromine is as a halogen source. So now the task is this one, that if I gave you the 3-hexene as a starting material or a hydrocarbon, and it is treating with NBS, and obviously in the same way that there will be the light induced reaction in the presence of in the solvent system, which is a dichloromethane. So you have to predict that what are the possible product or products formed when 3-hexane is treated with NBS. So the hint I have given to you that you have to go for more stable radical formation, favor attack of bromine to that position. You know which one is the most stable. So the tertiary one is more stable as compared to the secondary, and secondary is more stable than the primary one. And above all, you have to firstly look at what are the possible opportunities. What are, is there only one side, or is there more than one side where there is allylic carbon, and that allylic carbon hydrogen bond can be broken, right? The next thing is this one, that in your product, which one is your major product. So the major product in case of the alkenes is always that one where you have the most substituted alkenes. So the terminal alkenes are not the stable or the major products as compared to the most substituted. Whenever the double bond is a substituted one, so that is more stable form. As in the 3-hexene, you can see, because this double bond is not in a terminal position, this is just in between, and this is substituted from the both sides. So this is a stable entity, right? So in a similar way, by using these hints and keeping that points in your mind, so you can easily go for, and you have to draw the mechanism of this one with the 3-hexene as we did with the propene, to illustrate that you get that concept, and you have to draw and mention all of these 3 steps, and to predict the product. If there is more than one product possibility, then you have to mention that as well. So that was for today. So I would love to answer you, and you can comment even on a video under the video below, and we can have a discussion, and I can just confirm your answers. And otherwise, the registered students can submit their task on Moodle. So have a good day. Take care.